So in today's video, we're going to look at the chi-square test for association. What this looks at, it's our last topic that we're going to look through. What this looks at is our two different variables, okay? They're going to be two different qualitative variables, okay? For example, you could do gender and type of music, okay? That's two types of qualitative variable. Each one has multiple different things that it can be. So gender can be male or female, type of music, you can have country, jazz, classical, etc. Okay. What we're going to look at is the link between these two qualitative variables. Are they independent? Are they dependent? Does gender affect the type of music that people like? Okay. So that's the type of thing that we're going to look at with this chi-square test for association. And the way that we do this is by using something called a contingency table. Okay. What a contingency table does is it tells you the number of people that fall into these categories. So for example, if you had a contingency table for gender and type of music, you could have male, female, and then let's just pick three types of music here: country, jazz, and let's say pop. Okay, so three different types of music, and we've got these two different genders. So what we're going to do is we're going to write in this table how many people are male and like country music. So however many people there were, you can write that in there. Then you write in how many people were female and like country music. Same with jazz and same with pop. So a contingency table tells you how many people fall into these categories. So you'll have how many fall into male and jazz, how many fall into female and pop, etc. Okay? So it tells you the link between the two variables. Each one of the variables that you have, each one of your qualitative variables, in this case gender and music, each one of those variables has multinomial distribution, okay? There can be two or more outcomes, okay? So in the case of music, you could have 10 different types of music. So it's a multinomial distribution, okay? Because there are multiple different outcomes here. So again, what we're going to do this time is to run a hypothesis test to see if these variables are independent or dependent. Whenever you do this, your null hypothesis always suggests independence. Okay? We're going to assume that these variables have nothing to do with one another until proven otherwise. So H0 is always that the variables are independent. And the alternative is that they are dependent on one another. Okay, in my previous example, that would tell me that gender did affect the type of music that people liked. Okay, so that is always the case with these. Okay, once you have your null and alternative hypotheses, you could do this the long way and run one of these hypothesis tests. Okay, so you could then write down what your significance level alpha was, okay, and then you could go ahead and find your test statistic. Now, the test statistic in this case is not an easy thing to find. It is actually a very, very awful looking formula. However, the calculator will do this for you, okay, so don't worry too much about this. I will write down what the test statistic is. We call it chi-squared, again, is the test statistic. And I will explain to you what this actually says. But as I said, you're not going to have to use this because your calculator will do all of this calculation for you. Okay. What this says, it's very much like the chi-square test statistic that we looked at last time. What this does, bearing in mind we now have two different variables that we're looking at that we want to compare to one another to see if they are independent or dependent. Okay. This Nij that is here, that is the number of people that fell in that category in row I, column J. Okay. So if we go back here, it would be the number of people that were in, if you had N3, 2, okay? If you had N3, 2, that would be the number of people that fell in row 3, column 2. So it would be the number of people in that particular cell in the table, okay? So each one of those Nij's is just the number of people in row I, column J in that table. This Enij is the expected number of people to fall into that particular cell. So we observed that there were Nij people in that cell. So however many people fell into that cell, that's how many people there actually were. But how many did we actually expect to fall into that cell? Okay. The way that that is actually calculated, again, you're not going to have to do this because your calculator will do it for you. But whenever you do Enij, so the number of people that you expect to fall into the cell Ij, row I, column J, okay, it's always the total number, okay, and then it would be the total for row I divided by that total times the total in column J divided by the total. So it's so total is the overall total number of people, okay? Then it would be the total number in row I divided by the absolute total times the total in column J divided by the whole total. So what that tells me, let's go back again. When you did this table, okay, I could add up all the people that fell into this row, okay, and the total for that row I would go here. Okay, in this case, it's actually the total for row 1. Then for each, you could do that for every single row. You could add up the total number of people that fell into that row, both male and female. Okay. Then you could do the same for the columns. You could add up all the males that were in this. So this would be the total for column J. Okay, you could add up all the people that fell into this column. So all the males that liked any type of music. And you could do the same for the females. Add up all the females. And that would be a total that would go here. So what you do, and over here would be the absolute total. So you could add up the total of all the rows, or you could add up the total of all the columns. It would come to the same number. But what you're going to do is you're going to take the total and then multiply that by the total of that particular row over the total, multiply it by the total for that particular column divided by the total. So the expected number of people to fall into a particular cell is given by that number. As I said, you are not going to have to calculate that, but it will ask you on Hawks what the expected number for a particular cell is. So you're going to have to know where to recognize it, but you don't actually have to go ahead and calculate it. But I'll show you how to do that in a minute. So as before, you're going to take that number in each cell minus the expected number for that cell. Then you square it and divide it by the expected number for that cell, which scales it back again, exactly like we did last time. And you're going to do this for every single column and for every single row. So what I'm doing here is I'm adding up these terms for each column and for each row. So C is the number of columns, R is the number of rows. Okay? So that will give you your test statistic. Then what you can do is you can compare your test statistic to the critical value. Now the critical value, very much like the last chi-square one that we did, okay, is going to depend on your significance level and your degrees of freedom. Whenever you do a chi-square test for association like this, your degrees of freedom is the number of rows minus 1 times the number of columns minus 1. So in our case here, I would have the number of rows minus 1 would give me 2. The number of columns minus 1 would give me 1. Multiply those two numbers together, I get 2. So I would have 2 degrees of freedom in this case. So when I looked up you're going to look up the critical value in the table if you need it, okay? When you look up the critical value in the table, in that chi-square table, you need the significance level alpha and you need the degrees of freedom, which is given by this, okay? So then once you've got all of this, you have your test statistic, you have your critical value, you can go ahead and you can either compare your test statistic to the critical value, or you can compare P, which you'll get from your calculator, that P value, to your significance level alpha. And very much the same way that we did in 16.2, you are either looking for your test statistic to be greater than the critical value. So that gives me that my test statistic is greater than the critical value. Or, as always, you can look at whether the p-value that you get for your calculator is less than the significance level alpha. And in both these cases, what I would do is reject my null hypothesis. So it's exactly the same thing that I would do as in 16.2. So I'm either looking for the test statistic to be greater than the critical value or p to be less than alpha, and then I would reject my null hypothesis. Any other values that I get, I would fail to reject the null hypothesis. So this is the problem that we're going to look at as an example. It says that a researcher wants to study the relationship between salary and gender. She randomly selects 316 individuals and determines their salary and gender. Can the researcher conclude that salary and gender are dependent? So we've been given this table that shows people's income and their gender, and we want to know, are they independent or are they dependent? Well, first thing to do is to get down what our null and alternative hypotheses are, so you actually know what you're testing. So as always with these problems where we are using this chi-squared test, where you're trying to look at the relationship between two variables, in this case, as always, the null hypothesis is going to be that the two things are independent, so we always have independence in our null hypothesis. So null hypothesis is that gender and salary are independent, and our alternative hypothesis always assumes dependence. So our alternative says that gender and salary are dependent. Once you've got those two hypotheses down so you know what you're testing, we can then turn to our calculators and we can see how we're going to test this using a chi-squared test. So when you're on your calculator, first thing that you need to do when you conduct a chi-squared test is to get that table into your calculator. Now, you don't do this as a table, you actually put this in as a matrix. So that table of values goes in as a matrix. The number one thing to remember here is you do not include the totals that are given in that table. You only put in the actual data values. So ignore the total column and the total row that they have put in that table. You are just putting in the table of how many people have a certain salary and their gender. You forget the row totals and the column totals. So the way that you do this on a TI-84, you're going to go to second, and this button here that above it says matrix. And it's going to bring up this screen. You're going to go across to edit, because you're going to edit one of these. And any one of these, I've got a bunch of matrices in here, but you can pick any one of these. So I'll pick A, because that's where I've put my values. And you'll see that you'll notice that there are two columns. So this is the male column and the female column, and then the incomes are the rows. So however many people were in each category, that is what I've put into this table. So I've ignored that column that had the totals in it, and I've ignored the row that had totals in it. So it's just the stuff that gives us the information of how many people fall into each category. Okay, so you're going to put this in as a matrix. Make sure that you get the matrix of the right size, so you have to actually type in 4x2 on your calculator, and then it will give you a matrix of the right size. So it's always the number of rows first by the number of columns. So in this case, we had 4 rows and 2 columns, so it's a 4x2 matrix. And you can then just go ahead and arrow down, and you can input each one of those numbers into your matrix, which is what I've done here. Once you have done that, you are good to go. Okay, you can actually run the test from here, because when you are running this chi-squared test, when you run it, you're normally looking at your observed values and the expected values. Now, when we ran the goodness of fit test, you had to figure out what the expected values were, and you had to put those in yourself as a list in your calculator. In this case, you do not need to do that for a straight up chi-square test where you are testing the relationship between two variables. What this will actually do when you run a chi-square test, as long as you have your observed values in a matrix, you can then tell it, hey, can you calculate these expected values for me and put it into another matrix? So all you do is you just quote it a different matrix to the one that you've put your observed values in, and it will actually completely format that matrix and put all of the expected values in for you. So you do not need to calculate any expected values. It's actually a really nice thing about the chi-square test. So what you're going to do from here, I'm going to quit out of this. Make sure you do quit out completely, because otherwise the matrix menu messes up. So quit out completely. And then you're going to go to Stat and across to Tests. And it's all the way down here. So the chi-square goodness of fit that we used in 16.2 is here. It's the one above it. Okay. Whenever you're testing the relationship between two variables, we're going to do the chi-square test. Now, in the observed matrix, I've put the matrix A. Okay. The way that you actually tell it to use the matrix A is to go into second and matrix from this screen. So you're on this screen and you want to tell it that your observed matrix is matrix A. Go to second matrix again, and where it says names, just click enter on the name of the matrix that has that list of observed values in it. Okay. Same thing with the expected matrix, but this time just quote any other matrix that isn't the matrix that you used for the observed values, because even if you've got values in this other matrix, it's going to override it. Okay, so for your expected matrix, I could just go to second and matrix, and I want to tell it to put my expected values into the matrix B. Okay, so as long as you don't have the same matrix for both of these, you're good, because it's going to override whatever's in this matrix B and actually put the expected values in it. And you're going to calculate. Okay, number one, this chi-square value, that is your test statistic that you could compare to your critical value. Okay, we're going to look at the critical value in a second. I'm going to show you how to find that on the tables. So chi-square, that is your test statistic. This p-value, as always, it's the p-value that you can compare to your level of significance, and that will tell you whether you're going to reject or fail to reject a null hypothesis. And the degrees of freedom, the way that we find that is by doing the number of rows in the matrix minus 1. So in this case, we had 4 rows in our matrix, minus 1 gives us 3. And then you look at the number of columns in your matrix and subtract 1 from that. So we had 2 columns, minus 1 gives us 1. Then you multiply those two numbers together. So 3 times 1 is 3. So our degrees of freedom in our chi-square test is 3. Okay. So this test will give you the test statistic. It will give you the p-value that you can compare to alpha to tell me whether to reject or fail to reject. In this case, I mean, this is a really small p-value. It's probably going to be less than any level of significance you're going to be given. So in this case, we're going to reject our null hypothesis most likely. And then the degrees of freedom is your last one. Something else, as I just said, when you did your observed and expected matrices, we put our observed set of values into a matrix. But then we just quoted another matrix as our expected matrix. And what it's going to do is it's going to fill those values up. So if I quit out of this and I'm going to go back into second matrix, if I go across to edit again and now go down to that matrix B where I said that that was going to be my expected values, it will have completely changed that matrix and put the values in here. So each one of these values is what you would expect for that particular category. So let's say I wanted to know how many males I expected to earn less than $25,000. That was my first entry in my matrix on the other one, okay? The number that I observed, I think it was around 36, that was the number that I observed, but I actually expect around 51 males to earn less than 25,000, okay? So you can actually just read off, if it says to you, what's the expected number of females that earn less than 25,000, you go to the appropriate value on this matrix where you have your expected value matrix. You go to the appropriate value, the appropriate row and column of the thing that you are looking for, and just read the value off from that particular matrix. Okay, so this is actually really useful because this chi-square test, not only can you run the test, but it will also run all of the expected values for you into a matrix, and then you can use that matrix to give you any expected value that you need. The only other question you're going to get that we need to look at is if you are asked to find the critical value, and that is going to be done using the tables on Hawks. So if it asks you to find the critical value for this particular problem, what you're going to do is you're going to go to tables on Hawks, and it should bring up this screen. Then you can go to chi-square, and it will bring up this massive table, okay? Now you need to take into account whatever your level of significance is, so whatever the alpha value is, and how many degrees of freedom you've got. That is what's going to give you your critical value. So let's say in our case that we had a 0.01 level of significance, okay, really small level of significance. We've already said that we've got 3 degrees of freedom for our problem. So our critical value would be 11.345. If instead it said to us that, again, we've still got 3 degrees of freedom for our problem, but it said that our alpha value, our level of significance, was 0.05, then 7.815 would be our critical value. So you can just read it straight off of this table, okay? Then we can think about, okay, are we going to reject or are we going to fail to reject? So remember, you are going to reject your null hypothesis either if P is less than alpha, okay? We actually had a really small P value for our problem, so most likely with any of these values here anyway, we're going to reject our null hypothesis. But the other way that you could tell that you're going to reject your null hypothesis is if your test statistic is greater than your critical value. Again, that is the case with any of these values, actually with 3 degrees of freedom, okay? If we had, let's say, an alpha value of 0.01, that gave us a critical value of 11.345, okay? We had a test statistic that was 13 point something in our problem, which is greater than our critical value, so we're going to reject our null hypothesis in favour of the alternative. And that tells us, because we're rejecting our null hypothesis in favour of the alternative, that we think that there is a dependence relation between gender and income. So we think that they are dependent on one another and affect one another.